So what we're going to do is we're going to try to today start our explanation for valence bond theory, which was something put forward by Linus Pauling. And Pauling tried to explain how these Lewis structures work, because Lewis actually just came up with a reason for why molecules bond covalently and how we can predict their right formulas. For a diatomic hydrogen molecule, for example, he said, I bet these hydrogens are going to bond together until they achieve an outer shell electron arrangement that's just like a noble gas. And for hydrogen, its nearest noble gas would be helium. So he said, well, if hydrogens have one valence electron each, and I know helium has two valence electrons, maybe these two atoms will bond together, so they'll share that pair of electrons, so we get to count the two electrons for each. So if they both have a configuration like helium, that's going to be how hydrogen's going to bond to make a stable molecule. So what's really happening? Okay, you have these electrons in the outer orbital of a hydrogen atom, which is a 1s orbital. Let's draw a picture of those. Here's a 1s orbital on the left hydrogen and a 1s orbital on the right hydrogen. What do these orbitals have? They have one electron in each. So in Lewis theory, and he didn't understand orbitals because they didn't have orbitals at that time. He predated that. He just said, why don't we take the dot structures and let's just move those together. So bink, now those two electrons in the middle can count for the left hydrogen and count for the right hydrogen, giving them noble gas configurations. And his little idea seemed to work really well in predicting the actual formulas of covalently bonded molecules. And people said, wow, I really think that's good. But nobody really understood why. And Pauling said, well, I think what's happening is now that we understand that electrons exist in orbitals, when these two hydrogens bond, it's the 1s orbital on the left hydrogen with the 1s orbital on the right hydrogen are now merging together, and bink, they merge into one brand new orbital. It's no longer called an atomic orbital. Why were these called atomic orbitals? Because they're orbitals on atoms. This, which now merges together into one new orbital, we call a molecular orbital because it's an orbital in a hydrogen molecule. And if you look at the very center where the really dark region is, the darker the region where they overlapped shows the space of highest probability of finding the electrons. So the electrons are located in this region of space way more than they are out here. And if the nucleus of the left atom is right here and the nucleus of the right atom is here, these negative electrons attract the left nucleus and the right nucleus, and they hold the two atoms next to each other, and we call that a bond. So this was Pauling's explanation for why Lewis theory works. If we just try one more example of that for you, a diatomic chlorine molecule, a little bit more complex. So a chlorine atom had 7 valence electrons, and so you would write chlorine with 7 dots, and another chlorine 7 valence electrons, a chlorine with 7 dots. And what did Lewis say? Well, I think those two are going to come together and share that pair of electrons. So we can count then 8 electrons for the left chlorine and 8 electrons for the right chlorine. They both have noble gas configurations. I predict that will make them stable. Why is that really happening? So now we go back to our first test. I mean, you draw those little dots around the chlorine. You should be able to do that. It's in the 7th column on the periodic table. What does that mean? In the outer shell of a chlorine, you have 2 electrons in a 3s orbital. And then what else is in the outer shell of the chlorine? The p sublevel. There's a 3px, there's a 3py, and there's a 3pz. So these dots are representing pairs of electrons in each of these different valence orbitals, with the 3px having only 1 electron in it. And the other chlorine is exactly the same. So what orbitals are actually doing the bonding here? The lone pairs are not. The 3s, the 3py, the 3pz are not involved in bonding because those aren't the orbitals that are going to combine together to share the electrons. It's only the 3px's. So let's see if we can draw a couple of 3px orbitals on a couple of chlorine atoms. So the p orbitals are dumbbell shaped, and if they're along the x-axis, they would be called the 3px. So the red orbital is the 3px on the left chlorine, and the blue one is the 3px on the right chlorine. So as the chlorine atoms come together, these two atomic orbitals will merge together. You have first a 3px with 1 electron in it on the first atom, and a 3px with 1 electron in it on the second atom. And as the chlorines approach, these two orbitals will overlap with each other, merge into a brand new orbital that will no longer be called an atomic orbital. It'll be called a molecular orbital. That's what's happening when these come together. They're sharing that pair of electrons. So the way that physically happens in real life is these atomic orbitals come together, bink, and they merge into one giant, really bizarre looking shaped molecular orbital. So that's a molecular orbital with 2 electrons, and look where the electrons are spending most of their time, right here. Where's the nuclei? Here's one nucleus. Here's the other nucleus. So all this negative charge here attracts the 2 nuclei, and it holds the 2 chlorine atoms together, right? I'm only showing you the bonding pair. Where's all those extra lone pairs? Well, they're still there, okay? Here's the complete picture. You've got a 3s orbital with 2 electrons in it. I have a pair of green dots. That's the 2 electrons up here. Then you have 2 electrons in the 3pz. That would be this pair. You have the 2 electrons in the 3py. That would be this pair. And then what's this? This is the 3px's that have merged together to form this molecular orbital, and the 2 dots in red are the electrons holding the 2 atoms next to each other, because those negative electrons attract the nucleus here and attract the nucleus there. So all the other electrons are still there. They're just not used to bond the molecule together, okay? So this was Pauling's explanation as to why Lewis theory works, okay? Now, watch this. Let's apply the same thing to a water molecule. Now, you've got to be well-versed in atomic orbitals to understand how this works. Otherwise, this is going to sound like blah, 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 blah for the next 25 minutes today, okay? So here we go. A water molecule, you would imagine, is going to bond by having 1 oxygen combined with a pair of hydrogens. Here's oxygen's outer shell. It has 6 valence electrons, a pair go in a 2s, and then the other electrons go in the 2py, 2pz, 2px, right? This could be the 2px, this could be the 2py, this could be the 2pz. So if we're going to draw the 2 orbitals that have single electrons in them, because those are the ones that are going to bond. This is the orbital here that can overlap with another electron to form a bond. This is the orbital that can overlap with another electron to form a bond. See how they're drawn in the Lewis, in the dot notation? They're drawn as a line? That's not true. Some of us have real trouble going from what we draw in a dot structure to what's really happening in the atom. Where's a py orbital? Where's a px orbital? Here's a pyx, here's a py. How are they related to each other spatially? They're related at 90-degree angles. That's why they're called the px and the py. They're on the x-axis and they're on the y-axis. So don't get hung up by drawing the dots around the letter O and then looking at those dots and go, gee, my unpaired dots are 180 degrees apart from each other. So maybe hydrogens are going to bond 180 degrees apart in real life. Not true. The px is a dumbbell orbital on the x-axis. The py is a dumbbell orbital on the y-axis. So if hydrogens are going to bond to oxygen, they're going to have to bond to these 2 orbitals. Now, on the Lewis structures, okay, the hydrogens, you'd have to bring them from the left and the right. This is a hydrogen with an electron in its 1s orbital, and another hydrogen with an electron in its 1s orbital. And to make the bonds that Lewis says happens to try to make noble gas configurations, each bond is going to be formed by combining a hydrogen 1s atomic orbital that has 1 electron with an oxygen 2p atomic orbital that has 1 electron. So the hydrogen 1s and the 2px will make a bond. And then on the right side, the hydrogen 1s and the 2py will make a bond. So if we push these together, bink, it's the 1s combining with the 2px to form a bond here. And it's the 1s combining with the 2py to form a bond here. Looks very linear. If you look at a p orbital, you might go, oh, one's bonding here, one's bonding here. But no, this is the 2px. One hydrogen will bond to this red orbital. This is the 2py. A second hydrogen will have to bond to that yellow orbital. So in reality, if you know the geometry of the p orbitals, you go, well, the hydrogens have to bond to each p orbital. So one's going to bond on the x-axis and one's going to bond on the y-axis. So let's take those hydrogen 1s orbitals and have them combine with those p orbitals. When they do, the atomic orbitals merge together and bink, forms a molecular orbital, bink, forms a molecular orbital, okay? Now, what would be the shape of the molecule if this really happened? Look at that molecule. Tell me what the molecular shape is, where the atoms are in relation to each other. What's the shape of that molecule?
It's bent.
With an angle of?
That would be, what was it, 100 and...
So let me take you back to your young days when you're in geometry, okay? So we're not even in chemistry yet. You were a young neophyte then. Here's hydrogen, here's oxygen, here's hydrogen. What's this angle?
90.
Don't overthink things. So if the two hydrogens bond with the px and the py, the shape of the molecule is bent, but the angle has to be 90 degrees, correct?
Yeah.
Yep. It's like, what's that old saying that Groucho Marx said? Who do you do? Do you believe me or do you believe your lying eyes? Look at your eyes. That looks like a 90-degree angle, right? So Pauling
Right.
realized that too. Pauling said, if the hydrogens really bond with the two possible orbitals in the outer shell of oxygen, the 2px and the 2py, that would predict the shape of the molecule be bent with a 90-degree angle. Miss Quigley, of course, is using future knowledge. The future Miss Quigley knew that molecules of water aren't 90 degrees. Molecules of water are like 109 or 105 degrees, something like that. So that's where the answer came from, but not according to where the atomic orbitals are geometrically in relation to each other. So this is a real problem. So Pauling, trying to explain Lewis theory, had trouble with a water molecule. He couldn't explain why a water molecule really had a 105-degree angle. Diatomic hydrogen, diatomic chlorine, no problem whatsoever. But this one seemed to pose a real problem. And so Pauling made a proposition. He said, I bet something's happening before oxygen and hydrogen combine to form water. And it's undergoing a process that we're going to learn about now. So Pauling derived this change that must be occurring in the oxygen and hydrogen atoms in 1939. And what he did is he took the wave equations or the wave functions for the electrons in the hydrogen and the oxygen atoms. And he took the oxygen in particular. He took the valence orbitals of oxygen, which is a 2s, 2px, 2py, 2pz. And according to Schrodinger, the electrons in the valence shell for an oxygen atom, 2 would appear in the 2s orbital, and that has a certain wave function associated with it. 2 appear in the 2pz, a wave function can be written for that orbital, and then 1 electron each in the 2px and the 2py. They had their own particular wave functions. Pauling said maybe those really aren't the correct wave functions for the valence orbitals of oxygen. So what he did is he proposed that you can add up those 4 different wave functions, divide them by 4, and get 4 average wave functions. It'll be slightly different. So he proposed that linear combinations of an atom's valence atomic orbitals can produce another set of equivalent valence atomic orbitals. So we actually changed the mathematics from the Schrodinger equation. Instead of saying the valence orbitals of oxygen are the wave function for the 2px, 2py, 2pz, and 2s, he actually, linear combinations just means add. He added those 4 wave functions together, and then he divided them by 4 to get the average. And he said, what if the oxygen atom really had 4 average wave functions that were created? You would therefore have 4 orbitals that are essentially all identical to each other, and maybe the electrons will go in those orbitals instead. This process has a name. It's called hybridization. It's the combining of 2 or more orbitals of different sublevels to make an equal number of hybrid orbitals of equivalent energy. And orbitals of equivalent energy are said to be degenerate. So the combining of 2 or more orbitals of different sublevels to make an equal number of hybrid orbitals of equivalent energy. So if we graph the energy of the orbitals that exist in the outer shell of an oxygen atom, and the outer shell of the oxygen atom is the second energy level, you have a 2s orbital that has its certain wave function. The 2px has its wave function, the 2py has its wave function, the 2pz has its wave function, the electrons wind up going here. He said, what if I take the 4 wave functions, add them up, divide by 4, and get 4 average wave functions? That process is called hybridization. Well, you're going to get 4 orbitals now that are all identical in energy, but their energy is going to be somewhere between the average of the 2s and the 2p's. And with more 2p orbitals, the average would be weighted up towards the 2p's a little bit. So you can see these 4 orbitals I've drawn here are a little bit closer to the 2p level than it is the 2s level. So if oxygen changed its valence orbitals into these 4 hybrid orbitals, Where would the 6 electrons go? Well, because of repulsion, the electrons will not pair up until they have to. So the first 4 electrons would go into the orbitals like this, and then the 5th and the 6th would wind up going like these, okay? He had a name for these new hybrid orbitals. So here's where the names come from for hybrid orbitals. Because you're combining one s orbital, right? There's only one. With how many p orbitals are there?
3.
So 1s and 3p. He called these Sp3 hybrid orbitals. So they're just saying S1, there's one S you mix together, 3 Ps, so P3 you mix together. So each of those orange dashes represents what we call an Sp3 hybrid orbital. So he said these 4 hybrid orbitals would be created. Now, what does an s orbital look like? An s orbital looks like a sphere, right? What does a p orbital look like? It looks like a dumbbell shape. Well, if you're creating an average orbital, what's the average between a sphere and a dumbbell? A sphere has one big lobe. A dumbbell has 2 equal lobes. These Sp3 orbitals are between the two. They have a big lobe and then a little lobe. They're kind of the average. When you talk about hybridization, we've heard the term hybridization actually has biological ramifications too. There are things called hybrid fruits. If you take an orange tree and then you take a branch from a tangerine tree and you graft it onto the orange tree, and this takes a generation now, you let it grow a fruit, you take the seeds, you plant that seed, and now when you grow a new tree, the new tree you grow from the grafting of the orange tree and the tangerine tree is not an orange tree anymore, and it's not a tangerine tree. It's not a tree that exists naturally. You've created a hybrid tree that produces a fruit, and the fruit is not an orange, and it's not a tangerine. The fruit is a
Tangelo.
Tangelo. There are no natural tangelos in nature. We created those by hybridizing oranges and tangerines. It happens in the animal community too. A donkey and a horse, right, can mate. When a donkey and a horse mate, you don't have a donkey or horse, you have a what?
A mule.
Yeah, that's right. If you're a biology major, you may know that. Or if you have an elephant and a rhinoceros, you know what you get when they mate? You don't know that one? That's an elephino.
Does that actually happen?
That was a
No.
joke.
That was a great
that was
joke.
the
Yeah,
Yeah, that was the highlight of the day right there, by the way, for you. Yeah, sorry. So these are called SP.
Or a lion and a tiger.
A what? Doesn't that come from Harry Potter or something?
Oh yeah, I have one of those.
Oh, good. Okay, good. Glad to hear it.
A lion and a tiger, you get a liger.
Oh, that's from Napoleon Dynamite, right? Way better than a Tygon, right?
Those are real though, right?
I don't think so.
No, they're real.
I don't think what? They're not.
They're real, apparently.
Yeah, they're like super big.
Yeah.
I'm gonna look.
Yeah, I
that
got
up.
off the
don't
black
believe you.
market from
Yeah, I don't know about that. Okay, well, anyway, that's biology. So if you take the 2s orbital, which is the spherical orbital here, the 2px in red, the 2py in orange, the 2pz in purple, if you add their wave functions, divide by 4, and then write the 4 new wave functions for the sp3 orbitals, and you graph them, and here's the big thing, when Pauling graphed them, he wound up showing where the sp3 orbitals arrange themselves spatially, and they look like this. What shape does that look like?
Clover.
I'm
it's
giving
like
a
a
better-
tetrahedron.
That's
Oh.
a tetrahedron. Oh my gosh. If you just average out the wave functions for the 2s, 2px, 2py, 2pz, you wind up getting 4 average orbitals. And I've only drawn the big lobe. Each orbital has a little lobe behind it, but that would have made the picture more complex. But the big lobes point at the 4 corners of a tetrahedron. So Pauling discovered that if he underwent this process of hybridization, or if he believed atoms do, they would make new atomic orbitals. These are still the orbitals just in the outer shell of an oxygen. We haven't made any molecules yet. The atomic orbitals, the 2s, 2px, 2py, and 2pz can change into the atomic orbitals sp3, 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 and sp3, but they're arranged in a tetrahedron with an angle of 109.5 degrees between them. Well, What's the angle in a tetrahedron? 109.5. What's the shape of a water molecule? The angle with 109.5. Oh my gosh, this must be what's happening. Pauling said, I believe when water's formed, the oxygen changes its valence atomic orbitals through hybridization into sp3 orbitals, and then it bonds with hydrogens to make the water molecule. Let's see how that works. So here's our oxygen atom if it undergoes sp3 hybridization. 2 of those orbitals have pairs of electrons in them. 2 of them have single electrons. If the single electron is in the purple and the red, those are the 2 orbitals that'll be able to bond to the hydrogens. So now when the hydrogen 1s orbitals approach it and they overlap with those purple and red orbitals, which are the ones that have 1 electron each bond will be formed by combining an oxygen sp3 atomic orbital with 1 electron with a hydrogen 1s atomic orbital with 1 electron. And so I'm going to overlap them. And when the atomic orbitals overlap, they bink, change into a molecular orbital. Bink, change into a molecular orbital. And now look at the molecule. Hydrogen, oxygen, hydrogen. What's the bond angle of the new Pauling predicted water molecule? Bent 109.5. If these repel a little bit more, then okay, they'll squeeze together and maybe be 105. But this exactly predicts a bent molecule with an angle of 109.5. And everyone went, oh my gosh, I bet this is what the valence orbitals on atoms are doing. They're acting as waves, making wave properties. They have wave functions that describe them. But I think their wave functions change in order to bond, probably because when you finally create the molecule, you're creating a molecule where all the electrons are now further apart from each other. They repel less. So probably VSEPR theory is probably forcing the central atoms to undergo this hybridization. And that way, when the molecule is created, it's going to be the most stable arrangement of all these different orbitals because they're spread out as far apart as they can be. Okay? So we believe most molecules are created by having the central atom undergo hybridization first, and then the outer atoms bond to them. Now, I want to make some comments about these molecular orbitals are created. I have the dark blue molecular orbital and the light blue molecular orbital, okay? If we focus in on the light blue molecular orbital, it applies to both, okay? Every bond that's formed when atomic orbitals overlap each other, in this case an sp3 overlapping with a 1s, form orbitals that are completely symmetrical around their internuclear axis. What does an internuclear axis mean? It means if you take the nucleus of the oxygen, which is right here, and if you take the nucleus of the hydrogen, which is right here, and you draw a line connecting those 2 nuclei, and if you imagine these orbitals spinning around that line, is it always going to look the same? If it is, we're going to say it's completely symmetrical. I thought of it like if you have a skewer or something like that. If you have a skewer, if you rotate that around, that's going to always look the same as long as each of the pieces of pepper and onion and whatnot are like perfectly symmetrical, right? Okay. So in this case, you spin that around, that orbital is going to be completely symmetrical. And they've decided to give a characteristic name to a molecular orbital that's created that's completely symmetrical. And this is also considered a bond, right? When the 2 atomic orbitals merge together to make this molecular orbital that's holding the atoms together. So this molecular orbital, this bond, is called a sigma bond because it's completely symmetrical around the internuclear axis. We're going to see other bonds later that are not, so that's why this will be relevant eventually. But this particular bond here is completely symmetrical around the internuclear axis, so it's called a sigma bond. The dark blue molecular orbital created on the top is also a bond. That's the bond between the O and the upper hydrogen. And if you draw an internuclear axis around the dark blue orbital and imagine it rotating around that red internuclear axis, it's completely symmetrical as well. So it would be considered a sigma bond also. Okay? So when you name bonds in molecules, you first name its symmetry. Both these bonds here have perfect symmetry around the internuclear axis. They're called sigma bonds. Then, after sigma, in parentheses, you name the 2 atomic orbitals that merge together to form them. So what 2 atomic orbitals merged together to form this? What orbital was this before it merged? That was a hydrogen 1s. What was this before it merged? It's not a 2ps or a 2p, or not a 2s or a 2px, 2py, 2pz, that was an sp3. So you merged a 1s and an sp3. And so for people to see what orbitals merged together to create that, you just write that after the sigma. So each of the bonds in this water molecule are called sigma sp3 plus 1s. You could write sigma 1s plus sp3. There's no correct order for that. Just make sure you name the two bonds that have merged together to make the molecular orbital that's bonding the atoms together. Okay? Questions up to this point?
I'm a little confused on the idea of symmetry here. Maybe
So
I'm just struggling to visualize it.
absolutely. So watch this. Here's a line. Okay? If I skewer a football and I rotate this around, is it always going to look the same? Pretend it doesn't have any like of those threads.
Yeah, it's always going to look the same.
That's perfectly symmetrical. Okay? Look at this. What if I had a shape like this, a half moon? If I rotate this around, is this perfectly symmetrical?
Yes.
I would say no, because this little point here and this little point here, as soon as you rotate it 90 degrees, the points are like out here and out here. That like this is sticking straight out towards you and that's going back. So here it's on the top, here it's on the bottom. If you rotate it 90 degrees towards you, this is in the front, this is in the back. So that's not symmetrical. Maybe I could have drawn that picture a little bit better for you. I don't know. If I can draw it, I couldn't think of anything else to do, but if we just do a stick, oh my gosh, that would be so much easier to do. Let's say we have a stick like this, okay? If you rotate that 90 degrees, the stick's coming out towards you and going back, right?
Yeah.
That's not the same anymore. It has to look the same every 1 degree you turn it. So this is not symmetrical because as soon as you rotate it a little bit, now it's sticking out towards you. It doesn't look the same anymore. But if you rotate a football 1 degree, it still looks exactly like that. It never changes. This is symmetrical. This is not.
Okay.
That makes sense?
Yeah.
So that's what we mean. If you combine this orbital with this orbital, well, it turns out when you rotate this, it's always going to look the same. That happens to be very symmetrical. Okay? So that's sort of what we're talking about, if that makes sense.
Okay. Yeah, that makes more sense.
Good.
So, Professor,
Yes.
we're not talking about the whole molecule.
the
We're
light
just talking about that.
That's the bond right there. Not
Okay.
the dark blue, the yellow, and the orange. Correct. Otherwise, that would
Okay.
not be symmetrical.
Okay.
Yeah,
That was getting me right there.
Perfect. Can you see my picture of the molecule up here now? Is that visible?
Yes.
Okay, good. Okay. Let's try 2 more molecules to apply what Pauling said to Lewis theory and see if we can actually come up with the right shapes of the molecule. Okay. So here's an ammonia molecule. Nitrogen in the central atom has 5 valence electrons. Where do those electrons go? 2 of them go in a 2s orbital, and then 1 goes in the 2px, 1 goes in the 2py, 1 goes in the 2pz. This is why nitrogen is going to wind up making 3 bonds with 3 different hydrogens. You can bond 1 hydrogen to the left, 1 hydrogen to the right, and 1 hydrogen to the bottom. Okay? Now, the 2s orbital will not be used to bond because it has 2 electrons in it. You need to have 1 electron in the orbital so it can pair up with an electron from another atom. So the 2s, I'm not going to even draw. I'm just going to draw the 2px, 2py, and 2pz. So think about how they are spatially. You had to do this on the last test, right? What's a 2px orbital look like? It's the p orbital on the x-axis. What's the 2py orbital look like? It's the dumbbell shape on the y-axis. What's the 2pz orbital? It's the dumbbell-shaped orbital on the z-axis. These are the 3 different orbitals that have 1 electron each. So when hydrogens come up to the nitrogen and they move into bond, the hydrogen 1s's are combining with the 2px, the 2py, the 2pz. Now, how do they bond? They bond like 90 degrees apart and then 90 degrees apart, then 180 degrees apart? No, this doesn't tell you the shape. You got to picture how the atomic orbitals are arranged spatially. So if 1 hydrogen is going to bond to the 2px, it's going to attach to the x-axis to the red orbital from the right. If you're going to bond to the 2pz, you have to attach to the z orbital from the top or the bottom. And if you're going to bond to the 2py, you have to bond to the lobe either in front or behind. So when these 1s orbitals overlap with the 2px, 2py, and 2pz, you're going to get a molecule that looks like this. What's the angle between any pair of hydrogens in this molecule? What's the hydrogen-nitrogen-hydrogen bond? And you pick any pair of the hydrogens, it always comes out the same. Can you tell me what that angle would be?
180?
No, because the
Oh, 90, sorry.
and the 2py and the 2pz are not 180 degrees apart from each other, right? They're 90 degrees apart. Does that make sense? So you get a molecule that has 90-degree bond angles. What did it say in our homework today? Does the ammonia molecule have 90-degree bond angles? That was that question I skipped, right? It said ammonia has an angle of 107.3. So that's not matching it. So when you form a bond here on the 2pz, form a bond here with the 2px, and form a bond here with the 2py, you get a molecule whose shape is actually trigonal pyramidal. You'd have to look at it upside down to see it. But the bond angles are 90 degrees. They're not 109.5 or 107.3. So ammonia cannot be bonding with a 2px, a 2py, and a 2pz. It doesn't predict or doesn't produce a molecule that has the correct shape that we know to experimentally be true. So Pauling said, I believe most central atoms will undergo my process of hybridization before they actually form their molecules. So we cannot have the nitrogen bonding with the 2px, 2py, and 2pz. It's going to have to bond with hybrid orbitals instead. These orbitals we talked about, which are called Sp3 hybrid orbitals. So the molecule we know in real life is trigonal pyramidal with a 7-degree bond angle. So therefore, this cannot be happening. Okay. So just like we did with the water molecule, we looked at the oxygen, which was the central atom. We looked at its natural valence orbitals, the ones predicted from the Schrodinger equation, the 2s, the 2px, the 2py, and the 2pz. And where do the electrons go? In this case, in a nitrogen atom, a pair will go in the 2s, and then 3 electrons will go in the 2p. Well, if you're bonding with the 2px, 2py, and 2pz, you're going to get a molecule whose bond angles are 90 degrees, which isn't right. So Pauling said, let's imagine what would happen if it underwent hybridization. So once again, we add all the wave functions of these 4 orbitals together, we divide by 4, and we get 4 new wave functions that are all identical to each other, which means we're going to get identical orbitals, which will be equal in energy, so they're going to be degenerate. I would draw their dashes all at the exact same energy level. And if you combine an s orbital with 3 different p orbitals, they just happen to call these sp3s. So how would nitrogen's electrons go into 4 degenerate orbitals? The first 4 would go bink, 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 bink to minimize repulsion. And the 5th one would have to suck it up and pair up and spin pair like that. So we still have 3 orbitals capable of bonding, but because they're sp3 orbitals, what's the geometry of those sp3 orbitals? Sp3 orbitals, if you actually graph their wave functions, and they point in the 4 corners of a tetrahedron. So this is how those sp3 orbitals are going to look, pointing at the 4 corners of a tetrahedron. If the purple orbital at the top is the lone pair, well, that can't be used for bonding. So the yellow, the orange, and the red sp3s, the ones with 1 electron each, can be used for bonding. And so the hydrogens, with their electrons in their 1s orbitals, can overlap with the yellow, orange, and red sp3s and form 3 bonds. Bink 1, bink 2, bink 3. And now we wind up having a molecule who has this angle of about 109.5 degrees between the atoms. So this forms a trigonal pyramidal molecule with the theoretical bond angle of 109.5. And if we realize that 2 electrons in the lone pair pull towards the nitrogen nucleus more, so they repel against these guys, so they force the red, orange, and yellows to be a little bit closer, then we can understand why the bond angle will be slightly less than 109.5 and the actual 107.3. So we've created 3 bonds. We have a red bond, an orange bond, and a yellow bond. Each of those bonds, if you draw an internuclear axis, would be completely symmetrical, so those would be called sigma bonds. Now, what atomic orbitals combine to make each of them? You just name one at a time. So this is combining, it was a 1s orbital on a hydrogen with an sp3 orbital on the nitrogen. So the red bond is a sigma sp3 plus 1s. The orange is the same thing, sigma sp3 plus 1s. The yellow is the same thing, sigma sp3 plus 1s. So each sigma bond in the ammonia molecule is conformed by combining a nitrogen sp3 atomic orbital with an electron with a hydrogen 1s atomic orbital with one electron. And when you do that, each of these bonds can be named by just naming their symmetry, which is sigma, followed in parentheses by the two atomic orbitals that merge together to make them. And we have them written right here. It's an sp3 from the nitrogen and a 1s from the hydrogen. So those are called sigma sp3 plus 1s. Let's look at one more molecule to finish up today. We're going to look at the methane molecule, which is CH4. Now, if you're going to draw the dot notation of a carbon atom, carbon has 4 valence electrons, but the way you were to draw the dot notation for this is you would draw it as a pair and 2 singles. Does that make sense? Why do we do that? Because you just memorize it? No, because it's supposed to represent where the electrons are in the valence shell of carbon. We have a pair of electrons in a 2s orbital. Then the other 3 orbitals, the 2px, 2py, and 2pz, electrons go in 2 of those. So this is actually the arrangement of the valence electrons in a free carbon atom. The problem with this is, if you try to make an ammonia molecule, that carbon only has 2 unpaired electrons. Shouldn't be able to make more than 2 bonds, which is an interesting phenomenon, right? The electrons are arranged like this. There's only 2 orbitals with single electrons. And so those 2 orbitals would only theoretically be able to make 2 bonds. People originally thought, gee, I wonder if methane should be CH2 because of this. Well, if we assume that the carbon does the same thing that the nitrogen and the oxygen did in the previous molecules, what if I hybridize these orbitals into 4 sp3 hybrid orbitals? I would get 4 orbitals of equal energy. They would be called sp3s. How would the 4 electrons spread themselves out in 4 degenerate orbitals to minimize repulsion? They would go 1, 1, 1, 1. And now carbon actually has changed its outer shell arrangement to a pair and 2 singles into 4 unpaired electrons, right? Because now the outer orbitals are these hybrid orbitals. You may have had in a previous chemistry class, could have been in high school, they were teaching you dot notations, and you could have drawn carbon's dot notation like this on the right, dot, 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 separate like that. And if you would have done that on the first test of this semester, I would have marked it wrong because the actual arrangement for a carbon atom in its free state is a pair in the s orbital and then 2 in a pair of p orbitals. But when carbon bonds, these orbitals cease to exist because they change the normal valence atomic orbitals into the hybrid valence atomic orbitals. And now the electrons are arranged like this. So sometimes chemistry textbooks just skip this whole middle step and they just tell you, just memorize carbon has 4 individual electrons and draw your dot structure like this. That was probably too much assumptions on their part and skip too much of the story. But now this is actually really what's happening when carbon's going to bond. It's now capable of bonding to 4 different hydrogens. And if the carbon undergoes sp3 hybridization, we now know exactly where those 4 orbitals are pointing spatially because you now know the geometry of sp3 orbitals, just like you should have known the geometry of 2p orbitals last test. One's on the x-axis, one's on the y-axis, one's on the z-axis. Well, sp3 orbitals point to the 4 corners of a tetrahedron. So now with 1 electron in each of these orbitals, they're all capable of making a bond to a hydrogen. And so the 4 hydrogen atoms can overlap with each of those, and you'll form 1, 2, 3, 4 bonds, and look at the shape of that molecule. This forms a tetrahedral molecule with a bond angle of 109.5. And if you want to, take 15 seconds and see if you can tell me the names of each of those bonds and see if you've picked up how we name those bonds from the previous couple of examples. And if you've done that correctly, you recognize that each of these bonds looks symmetrical if you draw an internuclear axis and imagine them spinning around it. And the two atomic orbitals that overlap to make each of those bonds are an sp3 from the central carbon and then a 1s from the hydrogen. Okay. Now, with VSEPR theory, we've learned that anytime a central atom has a steric number 4, you're going to have the orbital geometry as tetrahedral. What does that mean? Well, the moral of the story is from today that anytime you have a central atom that has a steric number 4, guess what its valence atomic orbitals are doing? They're changing. They're undergoing hybridization, and they're changing from an S, a PX, PY, and PZ into 4 equivalent Sp3 hybrid orbitals so that they can have 4 repelling groups attached to them, spread out to minimize repulsion, creating a molecule of minimal energy, which means most stable. Okay? And we'll actually go on tomorrow to talk about more types of hybridization that can occur that can create even molecules with other steric numbers and how that happens. Okay?